this video, we will see a problem on calculation of stresses on faces of a rectangle. For that, here we have a question. A rectangular pier, which is a column, is subjected to a compressive load of 450 kN. Its width is 1500 mm and depth is 1000 mm. Eccentricities of load with x-axis and y-axis are 250 mm respectively. Find the stresses on faces of the rectangle. This is the question. Whatever is given here, I'll write that in the form of data first. Let us get started. It is given that here we have a rectangular section. Next is subjected to a compressive load of, I'll write the value of load, P as 450 kilonewton. So it is 450 into 10 raised to 3 Newton. Then its width is denoted by B, 1500 mm, and depth is 1000 mm. Now eccentricities are given, and it is given that eccentricity of the load with x and y axis are 250. So a single distance is given. It means Ex and Ey, they are same, that is 250 mm. Question is to find the stresses on the faces of rectangle. So we will calculate that stresses on the face of a rectangle, and for that let us try to get the solution. Now in the solution part, first we have to draw the diagram of the rectangle which is given. Here B is 1500 and D is 1000. This is 1500 with 1000 mm is the depth. Here we have x and y axis respectively. Now it is given that the load is placed at 250 mm. So the eccentricity is with x and y axis. It means it is with respect to the x and y axis forming at the centroid. So 250 mm from x upward, 250 mm from y. So I'll say that the load is placed somewhere here. So this is Ex, eccentricity with respect to x, Ey, eccentricity with respect to y. Now both the distances are same, that is 250 mm, and here I'll mark the corners. This will be corner A, here B, this is C, and this is D. So after marking the corners, when I look into the question, they are saying to find the stresses on faces of rectangle. That is, here we have to find out how much will be the stress on face AD, stress on face CD, BC, and AB respectively. Now when we want to find the faces stress on the faces, it is clear that the load is not on the axis. If the load would have been on this axis, then we can say that the rectangular column is subjected only to compression. But here, since the load is eccentric, this column is subjected to both direct as well as bending stresses. So I'll say that since the load is eccentric with respect to x and y axis, therefore there will be direct as well as bending stresses induced in the section. So here there will be direct as well as bending stresses induced in the section. So the first thing would be direct stress, and for that first I'll calculate the area. So cross section area is given by A is equal to, it is 1500 into 1000, so that is 1.5 into 10 raised to 6 mm square. Now after getting the area, I'll say that therefore direct stress is given by load upon area. So therefore direct stress will be, load is given in the problem, it is 450 into 10 raised to 3 divided by area, we have found out 1.5 into 10 raised to 6. So hence the answer of direct stress, it comes out to be 0.3 Newton per mm square. Next we have to find bending stress, and here I'll say that since bending stress about x-axis, that will be sigma bx is equal to bending moment about x-axis upon section modulus about x. Keeping this as equation 1, similarly we have sigma by is equal to myy upon zyy, that is bending stress about y-axis is bending moment about y-axis upon the section modulus. Second equation. Now we need to know all these values to calculate the bending stress, starting with mxx. Therefore bending moment with respect to x-axis, it is given by mxx is equal to p into eccentricity with respect to x-axis. Here p is 450 into 10 raised to 3, eccentricity with respect to x, that is 250. So therefore bending moment about x axis, it comes out to be 112.5 into 10 raised to 6 Newton mm. So now after getting bending moment at x, I'll say that bending moment with respect to y-axis, that will be same 112.5 into 10 raised to 6 Newton mm, because the load is same and even the eccentricity is same. Ex and Ey both are 250 mm, even the load is same. Now after getting this, the next thing would be to calculate section modulus. Therefore section modulus about x-axis, zxx is equal to ixx upon y. Now Ixx is the moment of inertia for the rectangle about x-axis, that is BD cube by 12 divided by y. Y is the distance of x-axis from the reference axis, and this is y, which is nothing but I can say that is d by 2. Therefore B is 1500, D is 1000, From this I'll get zxx as 250 into 10 raised to 6 mm cube. Similarly, section modulus about y-axis, that is zyy, is equal to Iyy upon y. So here we have Iyy is the moment of inertia for the rectangle about its vertical axis, that is db cube by 12 divided by b by 2, because it is the distance of the y-axis from the reference axis, b by 2. So next, when I put the values here, therefore zyy is equal to, now d and b values, d is 1000, b is 1500, so 1000 into 1500 cube divided by 12 divided by 1500 by 2. From the calculation of this, zyy comes out to be 375 into 10 raised to 6 mm cube. After getting these values, we can put them in first in equation 1 to get sigma bx, then in equation 2 to get sigma by. So therefore, put mxx and zxx in equation number 1. So therefore, sigma bx is equal to mxx, it was 112.5 into 10 raised to 6 divided by zxx, 250 into 10 raised to 6. So sigma bx, that is 0.45 Newton per mm square. Similarly, put myy and zyy in equation number 2. So therefore, sigma by is equal to mxx, myy both were same, 112.5 into 10 raised to 6 divided by zyy, 375 into 10 raised to 6. From this, the answer is 0.3 Newton per mm square. Now the question was to calculate the stresses on the faces. So for that, what we will do, first I'll calculate the stresses at all the corners and then see what we have to do here. Now I'll start with D because load is closer to D. So I'll say that this is calculation of stresses on each corner So first, stress at D, I'll denote it as sigma capital D. Now if we look into the diagram, see, because of direct stress, the direct stress we have calculated first, direct stress will be acting at all the corners, because the effect of this eccentric load is first to produce direct stress, and that direct stress will be there on all the corners. So when I am starting sigma D, here first I'll write down direct stress. Now if I consider eccentricity with respect to x, because of the load there will be bending about x, and because of that D will be pressed, so there is compression of D, and here I have plus sigma bx, because in this chapter we take compressive stress as positive. Next, similarly, when we have eccentricity with respect to y and it is on this side, it will press point D, again there is compression of D, so here I have plus sigma by. Now putting the respective values, sigma d it was 0.3, sigma bx that is 0.45 plus sigma by that is 0.3. So here I am getting my first answer as it comes out to be, it is 1050. Therefore the answer is sigma d is equal to, it comes out to be 1.05 Newton per mm square. Now as this answer is positive, it means there is compression on point D. Next, after this, opposite to this corner, that is opposite to D, at B we would be having the less value of stress, and that will be sigma B is equal to direct stress minus sigma Bx minus sigma By, because it is opposite to the point, because load was closer to D, so D has maximum stress. Load is extreme far away from B, so B will have minimum stress. So here it is 0.3 minus 0.45 minus 0.3, so that comes out to be minus 0.45 Newton per mm square. And as this answer is negative, in this chapter we take negative value of stress as tensile. So here we have tensile stress. So now after getting stress at B, next I'll calculate stress at C. Here we have point C and direct stress will be there. First of all, direct stress is there at all the points. Next, here we have eccentricity Ex. Because of that, point C will be compressed. Because of eccentricity E, it will be compressed. So here I have plus sigma Bx, but because of eccentricity Ey on this direction, here eccentricity is producing a bending on dA, so C would be lifted. Here as we see, because of the eccentric load, A and D will be pressed, whereas C will be lifted because eccentricity is on this side. If Ey would have been on this side, then C would be compressed. Now C is in tension, so tensile stress, it is minus in this chapter. 0.3 plus 0.45 minus 0.3. So sigma C is 0.45 Newton per mm square, and as this answer is positive, it means it is compressive. After getting stress in C, next the last point which is left is point A. So stress at A will be, direct stress will be there on each corner. Next, if we look at point A, because of Ex, as the load is on this side, it is eccentric. D and C, they are pressed because of Ex, whereas A and B will get lifted. So there is tension at A. So minus sigma Bx. But because of Ey, if we see the load is here, it will press, it will turn and press A and D, so they are compressed. So plus sigma By, that is 0.3 minus 0.45, then here we have minus 0.45 plus 0.3. So therefore stress at A, that value, it comes out to be, it is, here we have 0.6 minus 0.45 and it is 0.15 Newton per mm square. And since this answer is also positive, so here we have compressive stress. Now after we have found out the stress at all corners, we can know that what are the stresses acting on the faces as it is asked in the question. So for that I'll have to draw the rectangle. Now here I'll mark the corners A, B, C and D. So first I'll start with A and D, that is this face. At A the stress is 0.15 and it is positive. I'll project it. So here we are having stress as 0.15. I'm taking this value as 0.15 positive. Then if we look at D, at point D, the stress was 1.05 and it was also compressive. So here we have 0.15, here we have 1.05, so it is greater. So here I'll project this upwards. So the stress is more at point D. Now I can join this. So at A it was 0.15 Newton per mm square. At D it is 1.05 Newton per mm square. The nature of both the stress are same. It means it is compressive and it is going on increasing gradually, as we can see here. So this much is the stress on face AD. Next, similarly I can get it for AB. At A again the value is 0.15. I'll take it as a value 0.15. But at B it is negative, minus 0.45. So I'm taking the y-axis exactly at half. Now here this value is positive. At B the value is negative. It means from positive we will go into the negative region. So here this line is crossing here. At A it is 0.15 Newton per mm square. At B the value is 0.45 Newton per mm square. But for A it is positive because it is compressive stress. Here also these both the stresses were compressive, so positive. But at B it is negative since it is tensile. So now here we have these triangles. The positive triangle is for stress at A because it is compressive. So compressive stress is positive here. At B the stress is tensile, so it is negative. In this chapter we treat tensile stress as negative. Similarly, I'll plot the stresses for face BC. At B it is 0.45. At C it is plus 0.45. So value goes from negative to positive region. So again the nature would be like this. That is, at B the stress is minus 0.45 Newton per mm square and at C it is plus 0.45 Newton per mm square. It means at C there is compression, at B there is tension. At last the face CD. On C it is positive, on D it is more positive 1.05. at C 0.45 Newton per mm square, at D 1.05 Newton per mm square. So here we have shown the effect of load, and with the help of that the stresses on each of the faces, and that was asked in the problem, and with this we complete the question.